Hello everyone, my name is Saurabh Kumar Mitro and today I will present our research title Performance Analysis of LSTM-based radar scanning pattern using under quantum noise limited sensing condition. This work has been accepted at IEEE CSPA 2026 conference. This research focuses on a very challenging problem in modern radar system. How well deep learning models perform when radar signals are extremely weak and dominated by quantum noise. This work is conducted by myself, Saurabh Kumar Mitro, MD Waqib bin Awal, and our respected supervisor, MD Hossein A. Haider, all from the Department of EECE, Military Institute of Science and Technology, Dhaka, Bangladesh. Let me briefly summarize the key idea of the paper. So here is the background and the motivation of our paper. We know that radar antenna scanning pattern recognition is critical for electronic intelligence and electronic warfare applications. LSTM-based model achieve high accuracy under standard sensing condition. The objective of our research is evaluating the performance of amplitude-based LSTM model under quantum noise limited environment. To conduct this research, we are doing our modeling and approach on developed a realistic simulation framework incorporating photon shot noise model using Poisson statistics, amplitude distortion, measurement error, missing pulse and outliers. Radar scanning pattern represents as time series amplitude sequence. Here we applied late interpolation within CPA followed by LSTM classification. And finally, we get the results, that is recognition accuracy degrades with increasing noise intensity. Performance converts towards random classification level under severe noise. Here is the implications. It emphasizes the challenge of maintaining reliable recognition in extreme noise environments. Now I am going to my introduction. Here radar scanning pattern. Actually, it identifies radar antenna motion behavior from received signal. So there are mainly three types of radar scanning pattern we mentioned here. That is mechanical scan radar MSR, one-dimensional phased array scan, two-dimensional phased array scan. So here is the significance of radar scanning pattern for electronic intelligence, electronic warfare, radar threat identification, cognitive radar system. To analyze the radar scanning pattern, the traditional technique are pulse repetition interval PRI, beam width variation, amplitude envelope analysis. But in modern science, it depends on deep learning approach. Can be included long short-term memory, LSTM, convolution network, convolution neural network CNN, recurrent neural network RNN. So here is some related work. First of them is radar clutter recognition using LSTM, radar signal recognition with LSTM, that is published in IEEE radar conference, radar motion recognition with RNN, LSTM, deep learning radar detection using LSTM. Here is some research gap. Most existing research actually assumes high SNR, and they are performing in stable radar amplitude measurement. But actually, the modern radar system, especially LPI radar, often operate in extremely weak signal environment, photon limited detection regimes. So in that case, the actual thing is radar amplitude become highly stochastic. Traditional envelope feature loss discrete information. So here is our methodology. We are doing our model on we have done our model on radar pattern, radar scanning pattern modeling, sequential radar signal representation. Then we use quantum noise limited sensing simulation, and dataset is generated under multiple noise scenario. Then we use pre-processing by using late interpolation. We used then we input this data on LSTM-based sequence classification. And finally, we evaluate our performance and get the result. So, first of all, I will explain the core methodology of our paper. First, we represent the radar signal as a time series sequence. As receipt pulse amplitude is denoted as, here is AT means amplitude at time, and T means total number of pulse. So essentially, radar signal become a sequence of amplitude values over time. This transformation is important because it allows us to apply sequence learning model like LSTM. However, under quantum noise limited condition, the amplitude become highly irregular. We observe missing pulse, spikes, and random fluctuations. Moving to our next slide. Now, one of the most critical aspect of the work is quantum noise model. In photon limited radar system, the measurement is governed by photon count statistics. This follows the Poisson's distributions, where n means detected photon count, lambda means expected photon arrival rate. The key difference from classical system is noise is signal dependent, not constant. This is fundamentally different from Gaussian noise, and it makes problem much harder. Now the topic is noise and measurement effect. To make our simulation realistic, we incorporate multiple types of sensing impairments. Here is Poisson short noise, receiver gain fluctuation, pulse amplitude error, missing pulse due to low detection probability, random outliers. Actually, noise amplitude samples are models as we use this theory, and here this effect simulate extreme radar sensing environment. So this is the technique of our dataset generation. For dataset characteristics, we use 3 types of scanning pattern, 3 radar scanning pattern classes, 600 samples per class, 1800 samples per scenario. For signal configuration, we use sequence duration 180 seconds, pulse rate is 10 pulse per second, total pulse per sequence is 1800. For scenario design, we analyze the worst condition, and we use pulse amplitude error 20%, 40%, and 60%. Amplitude frequency offset, we use the value of 0.8, 1.5, and 2.5. Here actually we applied the balanced data sheet for random baseline is 33.3%. So now this is the topic is pre-processing, that is late interpolation. So actually raw signals suffer from missing pulse, low photon count, Poisson short noise, amplitude spikes, and outlier temporal discontinuities. To handle this, we use late interpolation, that means least absolute deviation. Actually, why we use late interpolation? Because it uses L1 norm, so it is robust to outliers, reconstructs missing samples, preserves local temporal structure. So this is a theory for late interpolations. And actually, A denotes the observed noisy amplitude, and here the parameter A is reconstructed estimate. Now the term is CPI level processing. After interpolation, we apply CPI level normalization. So for actually why we use CPI level processing? Because it removes scale variation, it ensures numerical stability, focus on relative temporal pattern. So this is the theory for CPI level processing. Actually here we use the mean and the standard deviation within the CPI. Now I am talking about LSTM architecture. So actually we use a lightweight LSTM network designed specifically for this problem. For input, we use sequence length 16 CPI segment, and the feature is amplitude per second. And for architecture, we can describe that LSTM layer with 64 unit fully reconnected layer 64 to 32, that's called RE value activation, and finally we get the 3 output class from the 32 data set. Finally, we use softmax for classification, cross entropy for loss function, and we intentionally keep the model simple, avoid overfitting or noise limited data. So this is our training protocol. Here we use this theory, and for training configuration we used train test 90% or 10%. We use ADA optimizer, approach is 20 and best size is 32. Then we use a evaluation matrix, and here this is a theory to determine the evaluation matrix. Here mean standard deviation is reported across run, accuracy reported for all 9 quantum noise scenario defined by PA 20%, 40%, 60%, and amplitude frequency offset 0.8, 1.5 and 2.5 as I mentioned in earlier. So this is our experimental reproducibility. This is a data set and the actually experimental setup. Now finally we get this result, and this table actually shows the classification accuracy across different noise scenario. Each noise scenario varies in pulse amplitude error, amplitude frequency offset on important observation. The accuracy remains in the table. We can see that the different type of accuracy, and finally we get the overall accuracy, and we see that the accuracy remains very low across all scenario. Also, the standard deviation is around 1.8 to 2%, which means the results are consistent and stable across multiple runs. So actually we can interpret that this is not a random fluctuation. This is a systematical behavior, and we get this result that shows the term. So this is an heat map visualization. This heat map provides a clear visualization. As we see, accuracy stays close to 30% in all cases, and remember random baseline is 33.3%. So the model is performing almost like random guessing. This clearly indicates this model is unable to extract meaningful feature under this noise condition. So this is a comparative analysis. We compared our result from a paper research work of Zheng et al. So they have described about classical LSTM in classical radar system, but we simulate our data on quantum noise limited radar. So if we compare this scenario, they use ideal scenario but standard for high SNR and no quantum noise limited condition, but we use quantum noise limited condition and we get this value. And by comparing this, we can see that in classical radar condition deep learning model achieve high accuracy, but actually under quantum noise limited condition performance dropped dramatically. So this comparison highlights a critical insight. The problem is not the model, the problem is the data quality and physical limitations. So now come to the conclusion. To conclude, we analyze LSTM-based radar scanning pattern recognition under quantum noise limited sensing condition. So we found that short noise overwhelms amplitude features. Classification accuracy dropped to channel 30%. Therefore, reliable recognition become impossible using amplitude-only data. And most importantly, the bottleneck is information loss and not model complexity. So this is the limitation of our research work. So it feature scope only amplitude sequence considered, phase or multi-sensor feature excluded, and we use synthetic data only due to the insufficiency of data. So of radar measurement, hardware clutter or environment effect included. Fixed segmentation. Actually, here is then a fixed segmentation of 16 LED process interval. Alternate strategies are not explored, and limited architecture. Only single layer LSTM with 64 unit tested. More complex architecture, LSTM transformer graph based temporal network outside scope. So this reveal the future research scope. So we can use or coherent we can use phase or coherent detection for extra feature under low photon count. We use multi-sensor fission to combine data from multiple sources. We can use in future we can use advanced model like transformer, TCN, CNN, hybrid beyond single layer LSTM. We can use natural language processing technique like embeddings, attention for better temporal representation. We can test with real radar data. We can use adaptive preprocessing like dynamic LED, joint amplitude phase denoising, and we can use also information theory matrix to benchmark the quantum noise limits. So here is the reference that helps us to conduct this research. And thank you everyone. If you have any question, please feel free to ask. Okay, thank you everyone.